Well, as you saw on Moodle, I do have your exams graded, and I'll get those in your POs here after class. We have Wednesday off this week as far as meeting, but I will be making an extra lecture because of getting off for spring break early. Doesn't mean there's going to be any more homework than usual due for Friday, maybe about the same amount, but just to get in enough lectures to cover the topics well, I think it would be good for me to make an extra lecture on Wednesday that you should still watch. On Friday's quiz, no quiz today, on Friday's quiz you'll be quizzed both on today's stuff and the lecture that I make on Wednesday, the extra one. Today, lecture 22 is really going to be our last main lecture on group theory. Is that sad? Or is that happy? Maybe mixed emotions, let's put it that way. And in short, you could probably title this lecture as sort of a big picture of some more advanced topics in group theory. Topics that, if you haven't taken foundations of math during interim, you might consider doing those topics for your main paper in that class, if you've liked group theory so far at least. Consider that. So I'll talk some more about homomorphisms and the First Isomorphism Theorem and an application, a more advanced application of that, which might intrigue you, I think. And we'll get into some details on that. We'll talk about something called the Fundamental Theorem of Finite Abelian groups, and you will have some problems to work on for this. Not the most advanced problems that I could give you. I want to just give you some basic problems. And certainly the proofs in that section you can pretty much skip over unless you're really interested. Although one of our other camera people did the Fundamental Theorem of Finite Abelian groups for their Foundations of Math project. So you might consider doing that as well, getting more details about the proofs. Then we'll summarize some more advanced problems and topics, which include, we'll go into some more detail on the Sylow Theorems, and I'll also mention some other things. All right. Realizing maybe I forgot to put everything on this PowerPoint that I might use later on, but oh well. So what are a couple big theorems? We've seen this slide before. This is the First Isomorphism Theorem is one of them here. Let phi be an homomorphism, excuse me. Homomorphism from G to G bar. Then you can say that the factor group, or quotient group, G mod the kernel of phi is isomorphic to the image of G under phi. And you can even say what the isomorphism is. It's what you might call a natural isomorphism. It's kind of the only formula that you could even guess. And fortunately it does work. We're defining this new function, phi bar, on the factor groups. So the inputs are cosets, left cosets. Really remember with normal subgroups, the left cosets equal the right cosets. So you really can think about factor groups in terms of right cosets as well. But we always do it with left cosets. You got an arbitrary left coset of the kernel in G with representative little g. You want to map it to phi of little g. That's kind of the only thing you could even guess as what might work. And as you had in the exam, you can prove this is an isomorphism onto the image. If phi happens to be onto, then in fact this factor group is isomorphic to G bar itself, okay, which is a common kind of situation for you. Sometimes make phi to be an onto homomorphism. And then you can say that the factor group is isomorphic to the entire codomain over G. A related theorem is that normal subgroups are kernels. Every normal subgroup of G is a kernel of some homomorphism of G, perhaps more than one homomorphism. But you can give one example to be more specific. A normal subgroup N is the kernel of the projection homomorphism that I call pi and many other mathematicians call pi. Our book called it gamma. It's not the number pi, that's a function here, it's a homomorphism. From G to the factor group, it's the natural one. Take an arbitrary element of capital G, what's the most natural thing to map it to in the factor group? It's this left coset. The left coset of N and G containing little g. That's just the most natural thing to do here. So these two things are really setting up relationships between kernels and homomorphisms, or normal subgroups and kernels, you might say. Every normal subgroup is a kernel. And we already knew that every kernel is a normal subgroup. That was another fact. Every kernel is a normal subgroup. And then you can relate the First Isomorphism Theorem to that fact by actually forming the factor group. Remember, you can only form factor groups when you've got a normal subgroup. It's common to visualize what's going on here in a certain way. The groups and functions from the last slide can be related in what's called a commutative diagram. And this is the picture that I put on Moodle off the internet here. This picture. With slightly different notation, using a fancy phi here instead of an ordinary phi. So you've got the original group up here. You've got this homomorphism. I'll write it my phi this way like we've been doing here. Onto G bar, but, well, maybe not onto. Homomorphism from G to G bar. It will be onto its image. Which will be a subgroup of G bar. If it does happen to be onto, then the image will equal G bar. You've got this projection homomorphism. This image that I got off the internet, they put a couple arrows there. I don't typically do that. And maybe that's to emphasize that it's onto, that it's a projection. I'm not sure. Onto this factor group, G mod the kernel of phi. And the idea with the first isomorphism theorem is, in this kind of setup, there must exist an isomorphism from this group to that group. And that's what we call phi bar. And the fact that this, the following equation, this diagram is said to be a commutative diagram. And it's not the exact same meaning of commutativity that we typically think of, though it's kind of similar. You can go around this diagram from here to here in either way and you get the same thing. You can just apply phi, or you can first apply pi and then apply phi bar. Phi bar composed with pi equals phi. That's what it means for this to be a commutative diagram. Okay, you can easily check that. What is phi bar of pi of an arbitrary element little g? Well, pi of little g, remember, from the previous slide was the left coset containing little g, which on the previous slide was little g capital N, but in this context is little g kernel of phi. And then we already knew the formula for phi bar with the, so this equals phi of g. That was the definition of what phi bar was. So by definition, phi bar satisfies this equation. Okay. Commutative diagrams end up being useful in a lot of areas related to group theory and ring theory and field theory. And in particular, I'm thinking of a topic you could consider doing for foundations of math, but it would be pretty tough if you do decide to do it. It's called Homological Algebra. Essentially, it's the algebra of commutative diagrams in short. So here you have, for example, a commutative diagram that illustrates something called the snake lemma, because it kind of looks like a snake, I guess. I don't know. You can snake through the diagram any way you want, and you're going to get the same thing in the end. The zeros, the A, B, C's, A prime, B prime, C prime, those are all groups, or more general algebraic objects. And the arrows are all homomorphisms, essentially. Maybe isomorphisms. They could be onto, they could be one-to-one. And for example, if you start up at capital A and you apply the mappings in the orders that you see here, apply little a first, then F prime, then little g prime, you'll get over here. You could get from A to C prime in another way, and you get the same function. That's the gist of a commutative diagram. You could apply F, then B, then G prime, or you could apply F, then G, then C. You're going to get to the same group in the end. And it's going to be, in fact, the same function no matter which way you go. The diagram commutes. Any way you go, you're going to get the same thing. This all feels kind of just, when you first learn homological algebra, like just sort of abstract nonsense, you might say. Yeah, this is the kind of stuff that people call abstract nonsense that I talked about before. Here's another commutative diagram. So it doesn't feel like you're really doing much except just going around a bunch of diagrams. But it does have applications. It has applications most prominently to something called algebraic topology. Where you are essentially applying abstract algebra to topology. Topology being intuitively about deforming shapes and still getting what you would call a topologically equivalent new shapes, you might say. That's a very, very rough kind of description of what topology is. But algebraic topology is the study of how to use algebra, like group theory, to study topology. It gives you invariants for topology, and this homological algebra with these commutative diagrams is a fundamental tool in that area. Okay. You can do some pretty impressive things with it, actually. That's something you could consider doing for foundations of math as well. Of course, we have these properties of homomorphisms acting on elements. Once more, I want to re-emphasize the meaning of this one. That the preimage of an arbitrary element in the image of phi is really a coset of the kernel. I want to relate this to linear algebra, actually. And relate even the First Isomorphism Theorem to linear algebra. So I related it to differential equations before. That came up on the test. This time let's relate it to linear algebra. Let's consider more ordinary linear transformations, like this example, say. With the differential equations example, the homomorphism was a phi of y equals y prime minus y, where y was a function of t, say, and this was the derivative. That was the differential equations application. Here we're looking at really a linear algebra kind of application. Define t, it's going to be a linear transformation, and remember, all linear transformations are homomorphisms. If we're only thinking about vector spaces in terms of the addition operation, they do form a group under addition, ignore scalar multiplication. We will talk about vector spaces themselves later in the book here, but for the moment we're just talking about groups. Define a function from the external direct product of R with itself, which we've typically called R2, like in multivariable calculus, the plane, to itself, or to R, excuse me, by this formula. It's a linear function. It is a linear transformation. By the way, that can be represented as a matrix multiplication. In general, linear transformations are represented by matrices. If it's a linear transformation like this, the matrix would be a 1 by 2 matrix, which we hardly ever deal with, but that's what would go on. You would multiply that by a column vector and multiply in the ordinary way to get this function. It can be thought of as a linear transformation with a matrix. But here I'm thinking of it as a more ordinary kind of formula that we write in multivariable calculus. For an arbitrary real number, what is the preimage of that arbitrary real number? Well, it's going to be the set of points. I'll go ahead and write R2 and R2 so that t of xy equals c. So that's the set of points in the plane based on this formula where 4x minus 3y equals c. I'll go ahead and write one more time here. The set of points. Let's solve that equation for y in terms of x. If we do so, we'll get y equals 4/3 x minus c over 3. That would be the preimage of an arbitrary real number c. But what is that? How do you geometrically interpret that? Usually you think about that as being a line with a slope of 4/3 and a y-intercept of negative c over 3. If c happens to be 0, then we're talking really about the kernel. Line with a slope of 4/3 and a vertical intercept of 0. The kernel of this linear transformation, thought of as a group homomorphism, is this line here. Slope equal to 4/3. C equals 0. This is the kernel. This is the kernel of T, which in linear algebra we call the null space. What are the cosets? What are the other preimages? They are cosets. They're lines as well, but they don't go through the origin. For example, when C is 1, this is where C is 0 here. When C is 1, you're going to get a line that's going to be parallel. Still have a slope of 4/3. Its vertical intercept, here the y-intercept, when C is 1, is going to be negative 1/3. This is negative 1/3 on the y-axis. This is C equals 1. This is the preimage of 1. It is a left coset of the kernel. You could think of this as being gotta be careful here. What is one element that gets mapped to 1? Well, it would be, for example, the point 0, 1/3, 0, negative 1/3, excuse me. That negative 1/3 refers to the tick mark on the y-axis. The point itself has coordinate 0, negative 1/3. For example, you could write this coset as 0, negative 1/3 plus the kernel. You need to use additive notation here because the group operation is addition. That make sense? You could represent this preimage of 1 here as this left coset. It's not the only way you can represent it. What would be its x-intercept here? C is 1. The equation was y equals 4/3, x minus 1/3. What's the x-intercept of that? Set y equal to 0 and solve for x. 4/3 x will equal 1/3. Multiply both sides by 3/4. The x-intercept is 1/4. So this point right here has coordinates 1/4, 0. So you could also represent this left coset as 1/4 comma 0 plus the kernel. And I could keep going here. I could consider other preimages. They'd all be left cosets. You could represent them all this way, but they'd all be left cosets of the kernel. And how is this related to the first isomorphism theorem? T here is onto, by the way. It is onto the codomain. So by the first isomorphism theorem, if I take R2 mod the kernel here, I should get something isomorphic to the real numbers. Does that make sense? R2 mod the kernel by the first isomorphism theorem should be isomorphic to R. What's happening when you mod by the kernel, when you form this factor group? You're thinking of the cosets as being individual points in the factor group, right? The individual cosets themselves are elements of the factor group. Each of these lines is one element of the factor group. Each of those lines, it's like you're collapsing them all down to one point. Maybe a point on the line perpendicular to these lines here. Doesn't have to be perpendicular, but maybe that's the nicest way to imagine it. It's like you're taking every point on one of these lines and collapsing it, mapping it, projecting it with the pi function onto one single point on this line. This black line gets projected onto this one point. This black line, the kernel itself, gets projected onto the origin 0. Some other line would get projected onto that. The projection mapping, the pi mapping, is taking all the points in each individual coset and mapping it onto one point on the red line. And there's a little intuition about why this should be true. It's not a proof, but a little intuition. Another example, we could up the dimension by 1 for the domain. we could consider a function from R3 to R given by this formula. If you represented that as a matrix, it would be a 1 by 3 matrix with entries 4, -3, and 5. Onto R itself, for an arbitrary C, what again is this preimage? It would be a plane this time. Let's view this with Mathematica. T of x, y, z 4x minus 3y plus 5z. What's the way to visualize a function of 3 variables? You can make a contour map of it with contour plot 3D. You can't make an ordinary graph because you'd have to be able to visualize in 4 dimensions if you did so. What does this show? Well, just as, well, come to the board here, just as these things were level curves, which are straight lines of this function, so in 3 dimensions, for a function of 3 variables like this, you're going to get level surfaces, which will be planes that are all parallel instead of lines that are all parallel. Places where the function output is constant. And that doesn't look right. Oh, okay, I was just looking at it wrong. There they are, some planes. We can add more of them. There we go, a bunch of parallel planes. Those are the left cosets of the kernel for this function. And they become the elements of the factor group. And the factor group for this example would be isomorphic to the real numbers as well. Imagine a line perpendicular to all these planes going through the origin. The projection mapping would take all the points in any given plane and project it onto one point on the real line, going perpendicular to this. The kernel is 2-dimensional, it's a plane. So when you mod R3 by the kernel this time, you still get a 1-dimensional thing. Okay, so those are all cosets of the kernel. The kernel would go through the origin. And you can generalize these kinds of visualizations as well. Let me skip over the slide about properties of subgroups of homomorphisms. You should, of course, know these things, but I know for them for the future, too. Even though we're ending group theory for the lectures after today, this is still something you should try to keep in your mind. I think you will be able to, by the way, because we're going to start rings and fields, and similar ideas are going to come up in rings and fields. Okay, so I think it won't be too hard to remember because of that. Before we go on to that fundamental theorem of finite abelian groups, let's look at an advanced example of the applications of group homomorphisms. This is on page 203 of your textbook. It's essentially a proof that any group of order 35 must be cyclic. It's a pretty advanced proof. It involves, in fact, spans 2 examples in the book. Page 203 if you want to look there. Examples 16 and 17. But I look at one of these arguments and I say, wow, this is really cool. It's amazing how all these tools come together to allow you to do something pretty profound. Right? All these things we've been talking about. Homomorphisms, isomorphisms, automorphisms, factor groups, Lagrange's theorem, various other things, First Isomorphism Theorem, external direct products. They're all tools, but it's not so clear how they're useful. I mean, we've seen some uses in classification results so far. In trying to consider a group of order 35 and to see that it must be cyclic, it's not so clear how the argument could possibly work. But I do look at this argument and I say, wow, I would be amazed to be the first person to think of this. Okay, because it's so amazing how everything fits together. So let's go through the argument. It's going to be an outline. So suppose you've got a group of order 35. By way of obtaining a contradiction, BWOC, by way of contradiction, assume all non-identity elements have order 5 or 7. Because if any had order 35, you'd be done. Right? It'd be cyclic. So somehow this assumption is going to lead to some sort of contradiction, and therefore there must be an element of order 35. That's the big picture of the argument. The first step is to argue, reason out why there must be some elements of each type. In other words, at least one element of order 5 and at least one element of order 7. In fact, if there's one, there's going to be more than one. That's fairly easy because elements of order 5 come in groups of 4. There I'm using the word group in the usual way, not the algebraic structures way. Collections of 4 at a time, right? Because Euler phi of 5 is 4. That's Euler phi. There are 4 elements in U5, 1, 2, 3, and 4. And 4 does not divide 35 minus 1. Does not divide 34. Why did I subtract 1?
Is it the identity?
Yeah, take away the identity. There's 34 non-identity elements in G. 4 doesn't divide 34. So all those non-identity elements cannot all be order 5. Could they all be order 7? No, because elements of order 7 come in collections of 6, since Euler phi of 7 equals 6. And 6 does not divide 34 either. So there must be some elements of order 5 and some elements of order 7, which of course then generate cyclic subgroups of order 5 and order 7. And those subgroups do have to be cyclic because 5 and 7 are prime. And then you argue that if H happens to be a subgroup with order 7, it must be unique. It's not at all obvious, but we use a tool. We use the tool for the formula for the number of elements in HK. This is a pretty useful thing. This fact. And argue, do a quick little argument by contradiction. Suppose K was another subgroup of order 7, different from H. Then this set, HK, how many elements would it have? It would have 7 times 7 over something. Now, if H and K are distinct subgroups of order 7, their intersection must be just the identity. This must be 1. H and K are distinct subgroups of order 7. They could only intersect in the identity, because if any one generator was in both of them, it would really generate both subgroups. That would be 49, and that's a contradiction because there's only 35 elements in G. So there cannot be more than one subgroup of order 7. Would that argument work to say there's not more than one subgroup of order 5? No, because you get 5 times 5 over 1, which is 25, and 25 is less than 35. And remember, in general, this is not necessarily a subgroup. We're just talking about the number of elements in this set. It's not necessarily something that has to divide 35. But 49 is bigger than 35, so you can't possibly have more than one subgroup of order 7. And that makes it normal in G, actually, if it's unique. If it's the unique subgroup of order 7, it's got to be normal, because this thing, I did do a proof one day that this is always a subgroup of G if H is a subgroup. But if and it's got the same size as H, it's got the same number of elements. But if H is the unique subgroup of order 7, this must in fact equal H, no matter what A is. And so that, by the normal subgroup test, means that H is normal. Making something called the normalizer of H equal to G. We've never talked about the normalizer before. We talked about centralizers. What's the normalizer? Essentially, the normalizer of a subgroup H is the biggest subgroup of G in which H is normal. Say it again. The normalizer of H, visualize it this way. Here's G, here's H. The normalizer of H is the biggest subgroup of G, maybe it's all of G, maybe it's not, in which H is normal. So H is going to be normal in the normalizer of H. H may or may not be normal in G. It depends on whether the normalizer equals G. This would be true if the normalizer does not equal G. You can define it with set builder notation like this. You could say it's the set of all elements in G with the property that this thing equals H. So if H is normal in G, then in fact the biggest subgroup of G in which H is normal is G itself. Okay? Keep going. It's not clear where this is going to go. Since H is abelian, its centralizer. Centralizer is making an appearance here too. But not a centralizer of an element, a centralizer of a subgroup. What's the centralizer of a subgroup? Centralizer of an element is the set of all things in the group that commute with that element. The centralizer of a subgroup is the set of all things in the group that commute with everything in the subgroup. Which can actually be written like this. Because this equation here is equivalent to saying xh equals hx. Kind of a similarity between these two things. They're not the same thing, but they're kind of a similar feel here. H is abelian, so everything in H commutes with everything in H. So the centralizer, everything in G that commutes with everything in H, must be bigger than H. It must contain it. It's a similar kind of picture. Except change the capital N to a capital C. And so, and these things, by the way, are subgroups. N of H and C of H are subgroups of G. That needs to be proved. And so by Lagrange's theorem, since H has order 7 and G has order 35, and that picture must hold, the centralizer either got to equal all of G or it equals H itself. So there's nothing in between. So 35 divided by 7 is 5 upon. If the centralizer happens to be G, meaning everything in G commutes with everything in H, then it turns out that this product, HK, has order 35, where K is an element of order 5. And remember, there did exist such elements. Because if everything in G commutes with everything in H, you'd be able to say that this property of exponents holds. Since K and H commute. Remember, that property of exponents does not work in general. It worked for abelian groups, and it does work when you've got two elements that commute. And that would allow you to prove the product has order 35, which would mean G is cyclic. You'd have your contradiction. We contradict the assumption that all non-identity elements have order 5 or 7, which means there would be an element of order 35. Constructed it too. But the assumption would lead to a contradiction. We're almost done. So that's one case, if the centralizer equals all of G. What if the centralizer equals just H? Then, turns out, okay, this would take proof that the centralizer of H is normal in the normalizer of H. Should make some sense if you think about it. And if this is true, then this factor group would have order 35 divided by 7, 5. But it turns out this factor group is isomorphic to a subgroup of the group of homomorphisms. That's coming into play. That's something called the NC theorem, which is the content of the example that precedes this example in the book, page 203, example 16. And the NC theorem can be proved pretty easily with the first isomorphism theorem. That in any group, G, with any subgroup H, the normalizer of H mod the centralizer H is isomorphic to a subgroup of the group of automorphisms of H. Wild. It's not clear that that would have any applications. But we're almost done. We're applying it right now. Because out of H, since H is cyclic of order 7, is isomorphic to odd of Z7, which we know from chapter 6 is isomorphic to U7, which has 6 elements. H is order 7 prime. It's got to be isomorphic to Z7. It's got to be cyclic. Order 7. Since ought is an invariant, ought of H would be isomorphic to ought of Z7, which by chapter 6 was isomorphic to U7. That's something you should have memorized for the test. That's got 6 elements. This has got 6 elements then. That's a contradiction. Because 5 doesn't divide 6, right? This thing's got to be order 5. It's also got to be isomorphic to a subgroup of ought of H by Lagrange's theorem. This would have to have order that divides 6. But 5 doesn't divide 6. You're done. That's a contradiction. So we go back to the original assumption that must be false. There must be an element of order 35. And any group of order 35 must be cyclic. Pretty tricky argument. It's hard. You know, I imagine the first person to discover this just had to do a lot of experimentation thinking about these different things. And just all of a sudden, maybe one day it popped out. It's like, whoa, that's pretty significant. That's pretty profound. I think I proved it. Okay? I think it's worth studying again, okay, and trying to appreciate how everything is coming together. All the tools are coming together to prove something kind of profound. All right. You're not going to have to do that for the homework, but it's worth reading. Here's something that does come up on the homework. Fundamental Theorem of Finite Abelian Groups. So I mean, this is chapter 11. And you could spend many lectures on chapter 11. You know, if I was going to do chapter 11 really thoroughly, I'd probably spend 4 lectures on it. It's that deep. The proofs are that challenging. I want to spend mostly just today's lecture on it. So we're just hitting the main fact. We're not going to prove it. And applying it to certain situations. It's called the Fundamental Theorem of Finite Abelian Groups. It says this: every finite abelian group is a direct product. They don't say whether it's external or internal. But maybe it doesn't matter, or maybe either one works. A direct product of cyclic groups of prime power order. Moreover, the number of terms in the product and the orders of the cyclic groups are uniquely determined by the original group. Proving this is very challenging. The text breaks the proof down into a sequence of lemmas. Remember, lemmas are facts that should be proved, that in and of themselves don't necessarily seem so useful or important, but they are useful in proving something bigger, something more important. Turns out this theorem can also be generalized to not just finite abelian groups, but what are called finitely generated abelian groups. I won't say what those are, other than just to allude to the fact that they include things like Z, which is cyclic, or the external direct product of Z with itself. Those are finitely generated. Maybe that's not so surprising. That's generated by one element. This is the external direct product of finitely many infinite cyclic groups that are each generated by one element. It does not include things like R. That's not finitely generated. I'm not going to explain why. You can generalize it. But we in our text just focus on finite abelian groups. And from this you can also prove a corollary that is really a partial converse of Lagrange's theorem. It's a full converse of Lagrange's theorem in the case where the group is finite. Excuse me, finite abelian. If G is a finite abelian group, and M divides the order of G, then G has a subgroup of order n. Right, Lagrange's theorem says that any subgroup of a given finite group has order that divides the order of that group. It does not say that given a number, m, that divides the order of the group, that there must be a subgroup of that order. But in the case of abelian groups that are finite, that is true. What kind of problems do you have that are related to this? Well, essentially, most of the problems involve thinking about and maybe listing the possible isomorphism classes of abelian groups of various orders. Take, for example, order 8. What are the abelian groups of order 8? Certainly Z8 is one of them. That's the cyclic one. You'd put Z4, external direct product, with Z2 in that category. And it is different than Z8 since 4 and 2 are not relatively prime. This is stuff you know. Z4 is not isomorphic to the external direct product of Z2 with itself, so this would be a distinct one as well. Are there any more? Well, 8 is 2 cubed. In each case, we have a group of order 8 that is either cyclic or the direct product of cyclic groups of prime power order. This theorem would say there be no others. There are no other abelian groups of order 8. What about the abelian groups of order 27? 3 cubed. Well, there's the cyclic case. And again, the theorem says this has got to be isomorphic to a general abelian group of order 27 would have to be isomorphic to the direct product. Maybe there's only one factor in the direct product. Maybe it's just this. Think of this as being the direct product with a trivial group if you wanted to, but you don't need to. There can be just one group if it's a cyclic group here. Cyclic groups of prime power order. 27 is 3 cubed. Prime powers that divide 27 are 3 cubed, 3 squared, and 3 to the first. There's a non-isomorphic group to this one that also has order 27. And here's another example, and there would be no others, because there's no other prime power order that you could work with. In both of these examples, 8 and 27 are both a prime cube. Think about this for a minute or two. You realize for any abelian group of order equal to a cubic or prime, there would be only 3 possibilities. Abelian groups of order p cubed, p is prime, would be zp cubed, the external direct product of zp squared with zp, and the external direct product of 3 cyclic groups of order p. And by the way, as we've emphasized before, these are all you need to write down because, for example, you switch the factors around, you get another thing that is isomorphic to the original. You do not need to list both of these, but they're isomorphic. We're talking about isomorphism classes. Okay, let's make it a little bit more challenging. What about groups of order, oh, say 8 times 27? Maybe I should do an easier example first. How about 8 times 9? Abelian groups of order 72, 2 cubed times 3 squared. According to this theorem, we can break it down into a direct product that may have just one factor, the cyclic group of order 72. Oops. Well, okay. One of these options that comes from the theorem is cyclic, but it's not immediately obvious until you use a theorem from chapter 8. We can break it down to an external direct product of cyclic groups of prime power order, one of which would be Z8 external direct product with Z9. But since 8 and 9 are relatively prime, that is isomorphic to Z72, that is cyclic. That's one option. And what you can do essentially is consider the factors Z8 and Z9 separately and break them down into possibilities like this and then combine them together. So what I mean there is I could take Z8 and make a non-isomorphic group of order 8, Z4 external direct product with Z2, and then combine it with Z9 as well as another possibility. Or I could have 3 copies of Z2, external direct product with Z9. But I'm not done, because I can do something similar with Z9. I could consider the external direct product of Z3 with itself. And I can do that with each one of these 3 cases. I could consider the external direct product of Z8 with Z3 and another Z3. That's sort of redoing that case, replacing Z9 with Z3, external direct product with Z3, which is not isomorphic, because 3 is not relatively prime to itself. Go to this case. Once again, replace the Z9 with the external direct product of Z3 with itself. And then go to this case and do the same thing. So in each of these cases, we are coming up with examples that do fulfill the conclusion of the theorem. We've broken these things down into the external direct product of cyclic groups of prime power order in each of these cases. And if you think about it, because 72 is 2 cubed times 3 squared, there's no other possibilities. So there are 6 abelian groups of order 72 up to isomorphism. And it's no accident that 6 equals 3 times 2, where 3 is really the number of abelian groups of order 8, and 2 is the number of abelian groups of order 9. Z9 and Z3, external direct product with Z3. It's not an accident that the answer is 3 times 2. All right, let's make it a harder case. Let's make it a 3 cubed here. 2 cubed times 3 cubed, what's that going to be? 216. There's 3 groups of abelian groups of order 8. There's 3 abelian groups of order 27, 3 cubed. There should be 3 times 3, 9 abelian groups of order 216. And if I just replace these 9s with 27s, I'm partway there. 27, 27, 27. And if I replace one of these 3s in each case with 9, I'm continuing to be partway there and saving some writing. And now you've got 3 more cases. Keep this part the same and replace the Z9s with the external direct product of Z3 with itself. 3 more things to write down. That one. this one. And one more, this one. Nine altogether. Writing these things in terms of a lot of external direct products is, well, it would be kind of unpleasant if you had to try to figure out the orders of elements using the least common multiple fact. Because if you're thinking about an element in there, it would have 6 components. You'd have to think about least common multiples of this form. Yikes. So it would be nice to maybe modify this in such a way that we have a minimal number of elements in the external direct product. And we can do that because when the cyclic groups have order that are relatively prime, we can combine them. 8 and 27 are relatively prime. This external direct product is isomorphic to Z216. It is cyclic. Here, for example, 4 and 27 are relatively prime. And if I rearrange things, I could say the external direct product of Z4 and Z27 would be isomorphic to Z108. But 2 and 108 are not relatively prime, so I need to keep the Z2 separate. I could have also combined the 2 and 27, but this seems maybe better. Here I could combine one of the 2's with the 27. And write this, etc. I could keep going. Down with this last example, each Z2 could be combined with one Z3. I could write this last example here as the external direct product of Z6 with itself again. It would be isomorphic to that. So in terms of thinking about orders of elements, that's probably a better thing to do. It's not fitting the way the theorem is stated when cyclic groups of prime power order. But for the purposes of using that fact from chapter 8, that's probably a better thing to do. To figure out the number of elements of order 4, for example. On the next slide, I do have an outline of what I just did. Little algorithm. Given an abelian group of order n, the algorithm to find the possible isomorphism classes of G. Step 1, find the prime factorization of n. So for 216, it's 2 cubed times 3 cubed. Step 2, find the number of partitions of the positive integer powers of these primes. What's a partition? It's not the same idea as a partition that we've talked about so far as breaking up a set into pieces, though it's a kind of similar idea. The partitions of integers, for example, 3, are the ways of writing 3 as a sum of integers, positive integers. You could just write it as 3. A sum is one thing, one positive integer. You could write it as 2 plus 1. You could write it as 1 plus 1 plus 1. Of course, you can also write it as 1 plus 2, but because of commutativity, we don't distinguish that as a distinct partition. So there are 3 ways of partitioning 3, writing it as a sum of positive integers, where the order is unimportant. There are 3 partitions of 3, corresponding to the fact that there were 3, put down here, abelian groups of order 8, 2 cubed, 3 being the exponent of the 2. Z8, Z4 with Z2, 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 Z2. 3 is also the exponent of the 3 here. There are 3 ways to partition 3 again, and there are 3 groups of order 27 that are abelian up to isomorphism. Z27 itself, Z3 with Z9, and Z3 with itself 3 times, corresponding to the way we did it with 8. Again, it's the exponent that's the important thing. What if the exponent was 4? What if we were thinking about the abelian groups of order 16, for example? So 4 is the exponent that we're talking about here. What are the partitions of 4? There's 4 itself, there's 3 plus 1, there's 2 plus 2, there's 2 plus 1 plus 1, there's 1 plus 1 plus 1 plus 1. There are 5 partitions of 4. 1, 2, 3, 4, 5. Order doesn't matter. 1 plus 3 is considered to be the same as this. 1 plus 1 plus 2 is the same as that. And there are therefore also 5 isomorphism classes of abelian groups of order 16. There's Z16. There's the external direct product of Z8 with Z2. Notice 16 is 2 to the 4th. Notice 8 is 2 to the 3rd, and 2 is 2 to the 1st. There's the external direct product of Z4 with itself. Notice that 4 is 2 squared. There's this external direct product. 4 is 2 squared. 2 is 2 to the 1st in both cases. These are the exponents of the primes here. And the last one, you have all 2's, corresponding to all 1's in this partition. Think about more examples, you'll see it making sense. Try thinking about abelian groups of order 32 and partitions of 5. Maybe I should quickly write down the partitions of 5. How many of them are there? There's 1 there, 5. There's 4 plus 1. There's 3 plus 2. There's 3 plus 1 plus 1. There's 2 plus 3 has already been used. Am I missing any there? There's 2 plus 2 plus 1. And 1, 2, 3, 4, 5, 6. There's that. And then there's 1 plus 1 plus 1 plus 1 plus 1. 1, 2, 3, 4, 5, 6, 7 partitions of 5. There would be 7 abelian groups of order 32 because of that. Think about examples that'll make sense. When you multiply the number of partitions, you get the total possible number of isomorphism classes. So, as an application of that, if you had a group of order 2 to the 5th times 3 to the 5th, there are 7 partitions of 5. You do that with both 2 to the 5th and 3 to the 5th. Altogether, you'd have 7 times 7, 49 different isomorphism classes for groups of this order. Since there's 7 partitions of 5 in each case. Altogether, you'd have 7 times 7, 49 groups of this order, abelian groups. We are talking about abelian groups here. Not even considering the non-abelian groups. Step 4 uses the techniques that I showed you to write them in various ways. Okay, we did that. All right, we've got 10 minutes. Let me quickly overview some other topics you might consider doing for foundations of math if you've not taken that yet. And if this stuff intrigues you enough to want to, do it. I'm going to spend most of the time in chapter 24, but I will highlight briefly some other chapters. Advanced topics in chapter 24. This is related to the Sylow Theorems, the chapter on the Sylow Theorems. A few technicalities. You don't need to write this down. I'm not going to quiz you on these things. Okay, just sit and listen. I'll quiz you on this stuff. Okay, but I'm not going to quiz you on this. Given an element A of a group G, you can create something called the conjugacy class of A by this formula. CLA means class of A. It's the conjugacy class. It's the elements in G that are conjugate to A. What does that mean? It's the sum of all elements of this form. We've seen this kind of thing a lot, right? X A, X inverse. X ranges over G. In linear algebra, if your group is a group of matrices, this has a different name. It's called the similarity class. Now, I haven't taught linear algebra in a number of years, but maybe, did you guys have Eric Gossett? Okay. Remember him talking about similar matrices at all? Ring a bell? It's talking about diagonalization and change of variables, that kind of thing. The two similar matrices have the same eigenvalues, for example, the same characteristic polynomial. They share properties. They're similar to each other. Okay, it's a similar idea here. No, actually, I did intend to pun. It's a similar idea here. Except it's just a different name. Conjugacy class instead of similarity class. Elements that are conjugate to each other might have similar properties. That's the idea. It does turn out to be an equivalence relation, so that the conjugacy class is partition group. And using that fact, you can prove that, in fact, the number of elements in a conjugacy class, which, by the way, is not necessarily a subgroup of the group, equals the index of the centralizer of that element in G. It's not a completely obvious thing, so if you're not sure where that comes from, you can read chapter 24. It's not super hard to see, but that's a fact. And because of that, it turns out that the number of elements in the conjugacy class of A, in the case where G is a finite group, divides the order of G. And something called the class equation is true. The order of G is the sum of these indices of centralizers, where the sum runs over one element from each conjugacy class. Interesting. G would have to be a finite group here. The order of G is the sum. It's not clear. It just seems like another tool. It's not clear where it's going to lead you. The first thing it does lead you to, though, is something, pretty interesting fact. If G is a P group, meaning G has prime power order, then the center is non-trivial. Talked about this kind of thing before with the GZ theorem, for example. The GZ theorem said if this factor group is cyclic, it implies G is abelian, which would actually mean the center would have to equal G. And it would also mean that that factor group would have to be trivial. This has a similar kind of feel. We did use this to prove that any group of order p squared was either isomorphic to ZP or was isomorphic to one of these two things. No assumptions about whether the group is abelian or not to begin with. This is something similar, except we're talking about perhaps higher powers. A group of order p cubed is not necessarily abelian, but it would have to have a non-trivial center. And in fact, if it was not abelian, the center would have to have order p. Excuse me. If G is a non-abelian group, with order p cubed, where p is a prime, the center can't be all of G, because then G would be abelian, and it can't be trivial because of this corollary, and it can't equal p squared because of the GZ theorem. Because if it equaled p squared, then the factor group would be cyclic, which would mean this was true and G would be abelian. That would be a contradiction. So you can conclude, for example, groups of non-abelian groups of order p cubed have to have centers that are cyclic. That might be useful. Okay, another tool. This all does lead to the Sylow theorem. We talked about Sylow's theorems. We talked about the first Sylow theorem before. It's a partial converse of Lagrange's theorem. G is a finite group and P is a prime. If P to the K divides the order of G, then G has at least one subgroup of order P to the K. If P to the K divides G, but P to the K plus 1 does not, then any subgroup of G of order P to the K is called a Sylow p-subgroup of G. So it's sort of a maximal subgroup of G that is an order, a power of P. So for example, if G has order 40, for example, which is 2 cubed times 5, a subgroup of order 2 cubed, 8, would be a Sylow 2 subgroup. P would be 2. And there would be no subgroup of order 2 to the 4th, since 2 to the 4th does not divide 40. And a subgroup of order 5 would be a Sylow 5 subgroup. Two subgroups are conjugate if this kind of equation is true. We've talked about that kind of equation before. Sylow's second theorem says that if you've got a subgroup of order of a finite group and its order is a power of a prime, then that group is contained in some P-low-C subgroup. The prime power may not be maximal. So any subgroup in this context of order 2 or 2 to the 4th would have to be contained in some subgroup of order 8. Maybe not so surprising, but it still takes proof. The proof of it's pretty interesting. It requires the orbital stabilizer theorem if you're interested. I think the coolest Sylow theorem is Sylow's third theorem, though. If the order of G equals a prime to a certain power times another number m that's relatively prime to P, the GCD of P and m is 1, then the number of Sylow P subgroups of G equals 1 mod P and divides m. Also, any two Sylow P subgroups are conjugate, and therefore unique Sylow P subgroups are normal. This has a lot more applications than you might imagine at first glance. Take this example here. Take the P to be 2, the K to be 3, and the M to be 5. 2 and 5 are relatively prime. The number of Sylow 2 subgroups would be those subgroups of order 8, 2 cubed, has to equal 1 mod 2. It's got to be odd. 1 mod 2. And it's got to divide m. It's got to divide 5. Odd divisors of 5. 1 or 5. There are either 1 or 5 Sylow 2 subgroups. That might be useful. And you could do something similar. Number of Sylow 5 subgroups. If we switch around the roles of these things, take P to be 5, K to be 1, and M to be 8, 2 cubed. The number of Sylow 5 subgroups has to equal 1 mod 5. It's got to be maybe 1 or 6 or 11. And divide M, which is 8. The only number equal to 1 mod 5 that divides 8 is 1. Any Sylow 5 subgroup of a group of order 440 must therefore be normal. That's probably useful. I know this is way too much to digest in a few minutes, okay? All I can do here is just say chapter 24 has amazing tools in it that can allow you to prove a lot of things. I don't have time to go over the other topics I wanted to talk about briefly. I hope, if nothing else, this makes you say, I'd like to learn those things, even if they might be challenging. At least if you do find group theory interesting. Okay, have a good day.